All right, this is what you should have gotten for the piecewise function. That was number 6. The red is the parabola. It went from 1 to negative infinity, so it's an open dot because it's not or equal to, and then it should have pointed to the left. Those 3 points need to be accurate, so it's not just an approximation. You actually need those points to make the curve. Then from 1 to 3, including 1 but not including 3, so solid dot on 1 but open dot on 3, is your horizontal line where y would equal 3. And then y equals negative x plus 6 results in that yellow line. It has a solid dot because it's greater than or equal to, and then it would point down to the right because the slope is negative 1. Questions on that one? Okay, then came the calculator one. So use the graphing utility to graph the function and then find the following information. From the graph, which looked something like this, I wrote all over it, but it looked something like this. My arrows point left and right, which means my domain was all real numbers are negative infinity to positive infinity. You're going to have to put that in interval notation. So all real numbers will not get you full credit for that question, negative infinity to positive infinity. Then the range is bottom to top. So I actually found the maximum first because that gave me the top point. So how you do this might go in different order than how the questions are asked, but eventually, and it's going to be the same on your test, you have to find the max, the mins, okay, because that's going to help you with your increasing and decreasing behavior. It's going to help you with your range. So that max on the right was, the y was 9.1. So my domain was negative infinity to positive infinity. My range, negative infinity to 9.1 with a bracket on the 9.1. And then your max and mins, the two maximums at the top were negative 1.2 and 7.3, and then 0.9 and 9.1. And there was only one minimum, which was negative 0.2 and 4.6. I didn't say what to round to. It does say on your test nearest tenth, so just keep that in mind.
How do you do minimum for stuff like that?
So when you get, let me see if I actually can erase this. I don't remember if I drew it on here. I think I did. Yeah. So when you do the minimum on your graphing calculator, you'll go second trace, you'll go to minimum, and then you have to isolate this guy here. So I'm going to do left bound around here, right bound around here, and then guess, and it will bring you to that point. It's not absolute minimum, but it is relative. Yeah.
So the test for like the graph like that like it goes up twice, those are both maximum?
They're both relative maximums. So absolute maximum is one max. Relative is every time it goes up and comes back down.
Is there like the test is going to ask you
Relative. It's going to ask you relative. No.
Okay.
Yeah.
Would the relative minimum for this one be also like the absolute minimum? Is there only one?
Yeah, but no, because your graph goes below that. So absolute minimum would be like a parabola that points up where it doesn't go below that point ever. Whereas this one, the sides go below that point. So it's not absolutely. Does that make sense?
Yeah.
Okay. Find the zeros. This is where that trace zeros comes into play. Negative 1.8 and 1.5 are where those happened. And then the value menu on your calculator is how you can find the f of 3.5, which is negative 446.9.
For number D for the zero.
I like that you just called it number D. Yes.
I didn't get I got super close, but I didn't get 1.8.
What'd you
I
get?
got negative 1.77.
But that would round to, yeah. On the test, it will tell you to round to 1.8.
Okay.
I mean, to round to the nearest tenth. So that's still right, yeah.
I put different numbers, and I don't know how. And then also for E, I put in like the value thing, and I put in 3.5, but I still got a different.
So check your equation then. Because that should definitely be the same. Like if it's still in your calculator, check it again. And if not, let's re-enter it. Yeah. Yes.
On letter D.
Yeah.
That's not in coordinate point form.
No, when you find zeros, you list them. If it said x-intercepts, you put it in coordinate point form.
Okay.
So your max and your min are in coordinate point forms, and your intercepts will be in coordinate point form. Anything that says value, you're listing, or zero, or roots, or solutions, you're listing. Yeah, you're welcome. All right, so we're getting into 1.4, which is shifting, reflecting, and stretching graphs. So we're going to talk about the parent functions first, and then we're going to talk about how these move around. These are approximations of your graph. So these are not exact. If it says to graph something accurately, you need points, that's different. This is graphing using transformations. So there are, I think I put 2 questions on your test on this stuff that will say, describe the transformations, graph, and then answer things like domain and range you'll still do from here. Increasing, decreasing, you can still do from here. So our general graphs, which start horizontal, so this would be like if f of x equals a number, okay? Obviously, that's your horizontal line. And then the identity graph or identity function is a y equals x or an f of x equals x. We're not going to do too much shifting on these, although it does exist, okay? You can still shift these the same way we shift everything else. Every single graph you should look at and you should be able to determine its domain, its range, and its increasing, decreasing behavior. So if you look at the first one, domain goes left to right, all real numbers. Range would just be the y that it runs through, which appears to be like a 1.75 on that graph, something like that. And then it is constant the entire way. No increasing, no decreasing. The identity function, domain negative infinity to positive infinity, range negative infinity to positive infinity. And this time it's increasing the whole time. So negative infinity to positive infinity, increasing. Yeah.
If it's constant the whole time, wouldn't you use brackets on them?
Because it's not a point. You're just saying what interval is it constant,
okay.
right? The range would actually get a bracket. So the range would be 1.75, let's say that is, with a bracket. Yeah, that's the only thing that gets it. Does that make sense? Yeah. Then you get the more common ones. So absolute value, square root, quadratic, and cubic. Your absolute value is a v with a vertex at 0. Your square root is that parabola turned on its side with a coordinate point at 0, 0, pointing up to the right. All of these technically have arrows at the end. Okay, I was just too lazy to try to get them on PowerPoint. The quadratic function or the squaring function is your parabola with a vertex at 0, 0. And the cubic function, it does constantly increase. So even though it kind of goes up a little bit, it would technically look like that. It's going to pass through 0, 0. It's like a parabola with the left side pointing down. So again, on these graphs, you should be able to tell me domain, range, increasing, decreasing, that whole thing. So what would be the domain on absolute value? What would be the range?
0 to 0.
Good. And it's going to be the same for your quadratic function too, okay? Where is it increasing? Good. 0 to positive infinity, parentheses on both. Where is it decreasing? Good. Again, parentheses on both. So that's true for both of those. For the square root function, what's your domain? 0. Good. To positive infinity with a bracket on the 0. What's your range? Good. Same. Increasing? Good. No decreasing, no constant. Cubic function domain? Negative infinity to positive infinity. Range? Negative infinity to positive infinity. Increasing. Negative infinity to positive infinity. It starts down and works its way up the whole time. So although it looks like it levels off inside that little space, it's constantly increasing. Good morning. So we will not do that every time, but realize that you should be able to do that every time, and the homework will tell you to do that on every graph, okay? All right, then you get the cube root function. These are not as popular, but they can exist. Cube root function takes that cubic function and turns it. It's like a square root 1 to the right, and then it flips it over the origin to the left, okay? Domain, negative infinity to positive infinity, range, negative infinity to positive infinity, and it is increasing on the entire interval. The reciprocal function is 1 over x, okay? And it looks like that. It has a curve in the top right quadrant and a curve in the bottom left quadrant. There's an asymptote at the y-axis, and there's an asymptote at the x-axis on this one. So the domain stops and starts. It goes from negative infinity to 0 because it can't touch this line. And then it starts again at 0 and goes to positive infinity. The range goes from negative infinity and stops at 1 because it can't touch that line. and stops at 0, and then it starts again at 0 and goes to positive infinity. It is decreasing on both intervals, from negative infinity to 0 and from 0 to positive infinity. And this one is your first odd function because it is, if you change this, actually these are both odd functions, okay, because they're both symmetric to the origin. Questions on either of those? Okay, so now let's talk about the different kinds of shifts. There is non-grid and grid. Grid means like you're literally moving it around, and then non-grid is where you're stretching it or shrinking it. So if you are adding, and it doesn't matter what the original function is, if you are adding after the function, so outside the absolute value, outside the parentheses, outside the square root, outside the cubic function, if it was the reciprocal function, it would be after the fraction. If you are adding or subtracting from these, it causes a vertical shift. We remember this, yes? The vertical shift is equal to that value. So if it said plus 2, I'm taking everything, shifting it up 2. If it's minus 2, I'm taking everything and shifting it down 2. So example 1, first identify your parent function. What would the original function be? X squared, which looks like a parabola. So if it says parent function and there's a line, you're giving me f of x equals x squared. That's the equation of it. If it wants to know what it looks like, it's a parabola or a U shape. X squared plus 1 causes what? Good, up 1. So I go up 1 and I make my parabola. These are just approximations. They don't have to be perfect. And then the minus 2 is a shift. Good, down 2. Pull it down 2. Draw your parabola. Now parabolas, the original U should be easy to find. If you go up 1 and to the right 1 and up 1 and to the left 1, you can plot those points to give your other x's, okay? But after that, outside of that, it could either grow quickly where it's narrow, or it could take its time where it's a little bit wider. All right, next is the horizontal shift. This happens inside the function. So inside the absolute value, inside the square root, inside the parentheses. If it was the reciprocal, it would be inside the denominator. And this is a horizontal shift, but in the opposite direction. So if it says plus something, I move that left. And if it says minus something, I move that right. All right, so what's the initial parent function for example 2? X squared, still parabolas. This minus 2 causes? To the right 2. So instead of it being at 0, 0, it's at 2, 0, and I approximate my parabola. For B, the inside the parentheses, x plus 2, causes what? Left 2, and the minus 3 causes a shift? Down 3. So it doesn't matter which one you do first. You can either go left and down or down and left. But I'm going left 2, down 3, and I'm drawing my parabola. So the only accurate point has to be the vertex so far. Questions so far? Okay, then comes the reflection. If there's a negative on the front of your function, so notice all of these are in front of it, a negative x squared, a negative absolute value of x, or a negative x to the third, or a negative square root, it flips it across the x-axis. It flips it upside down. You can add in there the negative 1 over x. It would be the same. Flips it upside down. So your u points down, your v points down, your cubic function flips from going up to the right and down to the left to up to the left and down to the right. And your square root function flips it so that it points down and to the right. So upside down. You still shift everything else the same. So if it's a shift up, I shift it up and point it down. If it's a shift left or right, I shift it left or right and then point it down. The different reflection occurs if the negative is inside the function, okay? If it's inside the function, it flips it across the y-axis. Now, it doesn't really have too much of an impact on a lot of things. If you think about a parabola that looks like this, if I flip this from left to right, what happens? It looks exactly the same, okay? What will change is if it's inside the parentheses and there's a vertical shift. So if it's inside the parentheses, a horizontal shift, sorry. With a horizontal shift, it changes the impact of the horizontal shift. So there's two ways to look at this. One is normally this is a shift left 2, and then I'd have to flip it over my x-axis or my y-axis, which would put it over here. And that would be your end result. The other way to do it is flip the direction of that sign. That normally says move left 2, but the negative on the front of the x is telling me go the other direction, so I can move it to the right and I can plot my curve. So again, with a negative inside the parentheses, and this would, or inside the absolute value, because the same thing would happen, you can either flip it over the y once you've drawn it, or you can just go the opposite direction. With a negative underneath the square root, it drastically changes it because this only has one side. So if this is my original parent function, it goes the opposite direction. It points it left. This is a square root of negative x. It flips it over your y-axis, okay? So a negative on the front points it down. A negative on the inside square root points it left. Still good. All right, example 3. Now what's my parent function? A square root, which is the half the parabola turned on its side, or the little arc pointing to the right. So what's happening with A?
There's a shift to the left.
Left 1 and the negative on the front? Flips it which direction? Upside down or over the x. I'll take either. Like the language on this one would normally say reflected over the x-axis. Okay, but for this test, you can either put upside down or over the x-axis. Yeah, sure. So I'm going left 1, and instead of pointing it up and to the right, I'm going to point it down and to the right. How about B? What are the transformations here? Up 3 and good. Point it left or reflection over the y. So I go up 3 and I point it left. Questions on those? So go to that first one. Go to A. What's the domain on this guy? -1 to positive infinity. What's the range on this guy?
With a bracket though, no?
Bracket. Good job. Thank you. What's the range?
-infinity to 0.
Good. So it's coming up, which means that the lowest y is -infinity, and then it would stop at 0. It is decreasing the whole way, so it's decreasing from -1 to positive infinity if you're talking about increasing, decreasing behavior. Questions so far? All right, so this is where your verbiage changes a little bit from what you've done before, okay? This is non-grid transformations, and there are 2 types. A vertical, which is a vertical stretch or shrink is what we used to call this, and a horizontal, okay, which again is a horizontal stretch and shrink. If the value occurs in front of the function, so this would be like a 2x squared, okay? If it occurs in front of the function, then it causes a vertical stretch or shrink. If that value, we ignore its sign, so that's why it's an absolute value. If the absolute value of that number is greater than 1, it causes a vertical stretch, okay? That is the same as it's been. Like if you, in Algebra 2 Honors, we use the same language, okay? This time it's going to ask by a factor of what? So this is, if for example, this has a vertical stretch by a factor of 2. If I want to know what effect that does to my coordinate points, it takes the y and you multiply it times that value. The x does not change. It would leave the x alone. So notice if it was 2, 4, it would become 2 and then 4 times c. So whatever value you would get for x would stay the same, but the y doubles in this case, which makes it narrower. Like think about doubling a value. It's going to pull it, as if you put strings on your arrows and you pulled it from the top. It will make it narrower. And then if that value on the front, again ignoring its sign because it's absolute value, the sign is the reflection. If it falls between 0 and 1, so we're talking a decimal or a fraction that's less than 1, then we say a vertical compression. We used to say it makes it wide, okay? But it's called a vertical compression. If you think about the ceiling and the floor caving in on your function, it is compressing it vertically. It would cause your u to get wide. It would cause your v to get wide. It would cause a square root to flatten out, whereas the vertical stretch would cause it to be taller. And again, same factor, by a factor of c. So if I go back to the example, it would have been a vertical compression. By a factor of 1/2. You would still multiply it times the v, but instead of making that, multiply it times the y, instead of making that value bigger, it's going to cut it in half in this case, or it's going to make it smaller.
If you still plug in points, will it show the vertical
Yes.
compression?
Yeah. So if you were to plug in a point on there, it would automatically give you that stretch or shrink. The language, when you get into like the AP style questions, you won't have an original function. You won't actually have an exact equation. You would say f of x exists. And then it would say what happens to, so like it would be like f of x equals a function. And you actually wouldn't be given this, okay? But that's your parent function. So g of x would equal 3 times f of x. That's how it looks. What is that? And that is a vertical stretch by a factor of 3. And if it said g of x equals 1/3 f of x, now it's a vertical compression, because it's making it flatter, by a factor of 1/3. So you won't have values to actually plug in. That's the difference, okay? I don't think the vertical stretch is that different from what we talked about. What's weird is the horizontal compression and stretch. So think about what happens horizontally to let's say it's a parabola, okay? If I took strings and tied them to the arrows and I pulled them up, that would be a vertical stretch. It would cause it to be more narrow, right? So this would be my parent function. This would be like a 2 times the parent function. It causes it to be more narrow. Now think about what happens to my parent function. So let's say this is my original. And what happens if it's a horizontal compression? Picture the sides squeezing in. What happens to this? It also gets narrow. So a vertical stretch and a horizontal compression almost have the same effect. I'll show you on the next slide where it would be different, okay? But they almost have the same effect. So a horizontal stretch would pull it up, and a horizontal compression would squeeze it in, okay? So when you think about it that way, hopefully it makes sense that the language is different here. If it is greater than 1, It is a vertical stretch if it's on the front, but it is a horizontal compression if it is inside. And if it's a fraction in between 0 and 1, on the front, it's a vertical compression, but inside it's a horizontal stretch. So with a vertical compression, it looks a lot like a horizontal stretch. And a vertical stretch looks a lot like a horizontal compression.
So it's like the opposite, it's like flipped.
The language is the opposite, but if you think about the actual visual, if I squeeze something from the sides, it does almost the same thing as pulling it from the top. Does that make sense? Mm-hmm. And I'll show you, there's like on the next slide I put a graph so you can kind of see the difference should you be looking at a graph. But with something like a parabola, it almost will look the same. Unless you had exact points, you wouldn't know the difference. Mm-hmm. Yeah?
What did you say the horizontal stretch is similar
to the vertical compression. Yeah, because you're stretching it. Look, you're making it wide. Okay. The same thing would happen if I squeeze it this way, right? So then the difference on the coordinate points is that we divide the x. So instead of it being the y, we multiply the y if it's a vertical. And if it's a horizontal, we divide the x by c. So if my x, if my c is greater than 1, if it said f of x equals, let's do absolute value, 2 times the absolute value of x, that's a vertical stretch. If it says absolute value of 2x, that's a horizontal compression. That is this. And so I would take my x value and I would actually divide it by 2. And what that does is it makes it grow faster because I said normally I'm at 2,4, but now I'm at 1,4. So it makes it taller quicker. And then if it's a fraction, if it said f of x equals 1/2 absolute value of x, that would have been a vertical compression. That is now, if it's inside, a horizontal stretch. So it's spreading it out. It's saying where I was at 2,4, I'm now going to be at 4,4 because 2 divided by 1/2 means I double that x. Yeah.
What difference do the -2s on the outside or on the inside?
Outside is a vertical stretch or compression. Inside is a horizontal stretch or compression. So here this is your visual on an actual graph. And it's hard because you can't really do this with a parabola. They appear almost the same. But on something like this, if you look at the one on the left, the solid graph is my parent function, okay? Now what happened from that solid graph to the dashed line? Was it stretched top to bottom? Was it flattened top to bottom? Was it squeezed left to right? Was it pulled left to right? Squeezed left to right. So what would that be? A horizontal compression. Okay? So this is horizontal. Horizontal compression. Look at the one on the right. The red is the parent function. The blue is the transformed one. What's happening there? This is a vertical stretch. So whatever this function is, let's say it's stretched by 1, 2, it's 1, 2. It's twice the amount. No, it's 3 times the amount. It would be like saying f of x, well, whatever f of x is, g of x would equal 3 times f of x. It is stretched vertically by a factor of 3. Whereas the one on the left, it's going to be like a g of x equals f of 1/3 x. So it's happening inside and it's the reverse. The 1/3 would actually shrink it, whereas on the right, the 3 stretches it. Yeah. Sure. Questions? Because we're going to put it all together. Yeah. G of x is just the transformed function of f of x. So we don't know what this actual equation is, but that's our f of x. So then how do I change it? And that's what we were saying. You were in the restroom, but Bella had said, could you plug in points? So if I have the function, I certainly can. But the AP style questions are not going to give you what f of x is so that you can't plug in points. It's going to say if this is f of x, describe what happens with this new equation. Or here's a graph. What happened to that graph? Okay. All right, this kind of just puts just the stretch and shrink on it, and then the next thing kind of puts it all together. So these are now absolute values. What's my parent function look if it's an absolute value? It's a V. The 3 on the front does what? This is a vertical stretch by a factor of? Good. So if I start at 0, 0, and I would normally, if my absolute value is normal, my slope is up 1 and out 1. This time it's up 3 and out 1. And it would, if I compared it to my original absolute value, that should be narrower. How about B? Vertical compression, factor of 1/2. So at 0, 0 it stays, but instead of going up 1 and to the right 1, I go up 1/2 and 1. Nope, sorry, up 1 and out 2. So it is wider. Questions so far? All right, do the next two. This is what it's going to look like on your test. Identify the parent function, which means give me the original f of x equation, not the word for it. Then describe the sequence, and if you just take your statement there and you point to it, that's fine, okay? Then sketch the graph of the transformed function, and then I'll go back to D and we'll do D together. All right, what's the parent function of example 5? X squared. F of x equals x squared. Describe the sequence of transformations from F to G. So literally, I'm just going to point to it. But normally, like, this could be, it's not for this test, but it could be a multiple choice question where you have to pick from them a shift this way, vertically this way, blah, blah, blah. Or, like, as far as your test goes, I'm going to give you a line and you'll just describe it. I don't care if you use symbols like up, arrow, down, arrow. That's fine. Okay? So this 3 at the front is what? It's actually a vertical shift, even though it's at the front because it could be in both directions, right? That's a vertical shift up 3. The 2 on the front of the parentheses is what? A vertical stretch. And by a factor of what?
2.
Good. What's the -4 inside? Right 4. So if you want to do that, that's fine by me. Like, that's enough descriptive terms. Just make sure if you say reflection, it's over which axis. If you say vertical stretch or vertical, like whatever you're going to use there, vertical stretch or compression, and then horizontal stretch and compression. Did I answer your question? Yeah. Okay. All right. Then we go to the graph. So it doesn't matter what order I do the horizontal or the vertical, but I got to do both. Right 4 and up 3 puts my point here. It's a parabola, so it's going to make a U shape. It's going to point up because it's a positive 2, but it is a vertical stretch. So instead of going up 1 and out 1, I'm going up 2 and out 1. And it makes my graph more narrow than my original parent function. Yeah. Yeah. Well, we're going to start it now because it's going there anyways, right? Okay. Then 6, what's the parent function? Good, absolute value of x. We know that to be a v, so that's the shape, but this is the parent function. Describe the sequence. So what's happening with the negative on the front? Reflection over x-axis, which causes it to be upside down. So if we want a vertical representation, that's how it would be. The 2 here is what? Good. It's inside, so it's a horizontal, not a vertical, and it's a horizontal compression factor of 2. And then the -4 inside is what? Which direction? Right 4. So I'm going to go right 4, and I plot my point. It's not going up or down at all. It's going to point upside down, so it would normally look like this, okay? Which is a normal up, down one and right one if my slope was normal. But this time, it's reversing it. It's going to be a vertical compression, making it narrower. So instead of going up 1 and out 1, we're going up 2 and out 1. And then I draw my V. Vertically compressed, again, like the walls caving in on it. Yeah.
If 2 is like 1/2, it would be a horizontal stretch.
Correct. So instead of going 1, 1, I would go 1, 2 if you make it a half, or 1, 3 if it was a third. Yep. Good question. Horizontal. Well, this is a horizontal compress. He's saying, what if this was 1/2? Did I? Oh, no, sorry. That 1/2 would be a horizontal stretch. It would go 1 and 2 and 1 and 2. Vertical stretch by a factor of a half. Valeska.
Did you like move over 2, or did you move over 1 and down 2?
I moved down 1 and over 2. Because you're dividing your x by c. So if my x for this one, so that has a factor of 2, but the factor of 2 says take the x and divide it by 2. So you're making the x smaller, but the y stays the same. So I still want to go, does that make sense? Yeah. Okay. All right, then the last thing I want to show you, and this is just a tool, okay? This is Desmos. If you've never used Desmos, it's an online interface. It also has an app, but it's super cool when you're messing with manipulating graphs, okay? So it's you can get it, like I'm not even in my account, but you can get a free account and then it will save your stuff. But this is like, I literally just put in an f of x. That's a parent function. So I put in f of x, I hate you. I cleared it out. F of x equals square root, there was an x already. Okay, and that's my parent function. If I want to add to this and I want to see what kind of effect it's going to be, I can add another function. So I can add a g of x. And then let's say I want to see a horizontal compression on a square root. I can do square root of x. No, let me put the compression on there. 3x. And then I can even add on here like a vertical shift plus 2. And there it is. So this would be a horizontal compression because it's bigger than 1. It's squeezing it this way. And a vertical shift of 2. So it's just a cool way to see the manipulations visually in front of you. And I feel like this, typing it in, especially on a computer, is easier than typing them all in on your graphic calculator, okay? A reminder, tonight's homework is a PDF. You need to show the graphs. So you're drawing them by hand, and then it's asking you for domain, range, and increasing on all of them. I know it's tedious and annoying, but it's going to be the best way to practice what you need to do for your test.